So before we talk about the formula for the determinant, an important component of that is something that we'll call the sign of a permutation. And so for that, we need to talk a little bit about permutations. So a permutation of a set 1, 2, 3 up to n is really just going to be a bijection from the set to itself. Now that's one way of thinking about it. Another way of thinking about it is that you are really just placing an ordering on the elements in the set. So for example, if we had a permutation that looked like, from the set 1, 2, 3, 4, 5 to itself, let's say 1 goes to 5, 2 goes to 4, 3 goes to 1, 4 goes to 2, and 5 goes to 3. Then we can think about this also as being an ordering of the range elements in our permutation. So we would say, all right, 5 is going to be less than 4, is going to be less than 1, is going to be less than 2, is going to be less than 3. Now, obviously, this doesn't give us our traditional ordering of 1, 2, 3, 4, and 5. But it does raise an interesting question, that if we are allowed to swap any two adjacent numbers, then how many swaps do we need in order to convert this ordering to our standard ordering? And that is what we'll end up calling the sign of a permutation. So if we take our example that we just had of 5, 4, 1, 2, 3 being that ordering, we can say, well, how many of these adjacent swaps does it take in order to get back to our standard ordering? Well, if we just want to move 1 up to the first spot, then it's going to take 2 swaps to move it from into the second spot and then finally into the first spot. Then if we want to move 2 into its standard position, again it's going to take us 2 swaps to do that. And again we have 2 more in order to get the 3 into its position, and then finally 1 more in order to swap the 4 and the 5. And so to go from our first one to the last one takes us 7 swaps in order to do that. And since 7 is going to be an odd number, we say this is an odd permutation. Now, another way of looking at these swaps is in terms of the transpositions of our functions and doing function composition. And so we can think of this bijection as being a composition, or we can break it down into a composition of simpler permutations, which we call just transpositions. So we can think of a permutation as a transposition as really just being a permutation that swaps 2 elements and leaves everybody else alone. So formally, it's going to have this definition to it, where if we have our input value k, as long as that k is not equal to 2 distinct values I and j, then it's going to be the identity element. So it's just going to return the values that you put into it. But on the other hand, if we put in I or j, then if we put in I, it's going to return us j. If we put in j, it's going to return us I. And so in essence, this thing just swaps our I and j values. And so a permutation is really just kind of a pretty simple example of transposition is really just a simple example of a permutation where you're only swapping 2 particular values. Now what we want to do is to take this permutation that we have, and we want to write that as a sequence of compositions of transpositions. So we can think of these transpositions as being kind of the simplest permutations that we can possibly have. And so we want to kind of get a measure, if you want to think about it that way, as to how far away from, or how many of simple transpositions does it take in order to get to this more complicated one. So it kind of gives us, I guess you can think of as a measure of complexity of the permutation, or how maybe long or complicated it might be. So going back to what we just wrote with our orderings, in essence, we have done that because we have just swapped two particular values. Now, if we go through and we just get rid of our inequality signs, and we can replace our connections with just arrows to kind of give us what would be a function or a biject. So we would have 1 going to 1, 2 goes to 2, 3 goes to 3, and we swap 4 and 5. So this becomes our first transposition, tau sub 1. Then we do the same thing and just kind of keep it going. 1 goes to 1, 2 goes to 2. Now we swap 3 and 5, and 4 stays where he is. And that gives us our second transposition, tau sub 2. And we just keep this process going all the way up until we end up with our sequence of transpositions, so that for our original function sigma, we've actually written now sigma as being our tau 7 composed with tau 6 composed with tau 5 composed with tau 4, tau 3, tau 2, and tau 1. So we've written this composition, or we've written this more complicated permutation as this sequence of kind of simple transpositions. Now, the only problem with really doing this is that there's not really one unique way of doing this. There's actually could be several different ways of doing it. We just picked one particular ordering. We could actually have an entirely different sequence of these things that moves from our original permutation to our standard ordering. And so one complication is that the way of doing this isn't really unique. But something that we do find out of this is that for any two sequences that we might come up with, they will always differ in an even number of steps in how long it takes to go from the original permutation to our standard ordering. So that gives rise to a theorem that for any permutation sigma, if we write that permutation as a composition of transpositions, say tau sub 1, tau sub 2, up to tau sub k, then what we find is that the length of those sequences will always be either odd or they will always be even. And so that gives rise to this notion of calling permutation either odd or even. And the proof of this particular theorem you can find in pretty much any introductory abstract algebra textbook. And so that we will leave for a later discussion in a different class. So somebody could give us the kind of random permutation that we see here, and then we can be asked the question, is this going to be even or is it going to be odd? Well, that's just a matter of how many transpositions does it take in order to get us back to our original standard ordering. And so if we just take our first element 1, and we say, well, how many steps is it going to take in order for me to get 1 back to its standard position? And so 1 must move a sequence of 4 steps in order to get back to its original position. And so we have a sequence of 4 transpositions to get 1 back to its place. Now, how many transpositions is it going to take in order to get 2 back to where it needs to be? we can see that it's going to take 7 steps or 7 different transpositions in order to get 2 back to its original place. And so it will have a form that looks something like this. And likewise, it's going to take 4 transpositions in order to get 3 back to its place. And then to move 4 to its place is going to take 1, 2, 3, 4, 5 transpositions. To get 5 back into place is going to take 4 transpositions. To get 6 into place will take 2 transpositions. And this finally gets us back to our standard ordering. And so our total number of transpositions takes 26 transpositions. And so that tells us that our original permutation is even. So a little bit of notation. If we pick a natural number n, little n, then if we take the set capital N sub n, then that's going to be the set of natural numbers that will be less than or equal to n. Then our set sim n will just be our set of bijections from n sub n to itself. Now, just like we've said, this is really just going to be the same set of orderings on our set n sub n. Then for our sigma that happens to be in this set, we say that -1 to the sigma, so we'll define this symbol to be 1 if sigma is an even permutation, and -1 if sigma is an odd permutation. And so maybe one of the last things that we'll need in our discussion of the sign of a permutation is the fact that the signs respect composition of functions. So what that means is that if we have 2 different permutations, say sigma and sigma hat, in our group of permutations, then the sign of the composition of those 2 permutations is going to be equal to the sign of the first one times the sign of the second one. And so, even though we don't really have something that looks like multiplication in here, this is really composition, that it still respects the composition operations with the multiplication operation. And so to see why that's going to be true, remember that the sign means that we can write our permutation as the product of so many transpositions. So let's say the first one is written as a product of k transpositions, and our second is written as a product of, let's say, L transpositions. And so quite naturally, we can write the composition, sigma, sigma hat, as just the composition of both of our sequences together. So tau 1, tau 2, all the way up to tau k, and tau 1 hat, all the way up to tau L hat. And so we can see that that's going to be k plus L. Now for our sign, that's going to be, so -1 to the sigma, sigma hat. So the sign of our composition is really going to be -1 to the k plus L. But that is the same thing as -1 to the k times -1 to the L. And that -1 to the k, that was our sign of sigma. And -1 to the L was our sign of sigma hat. And so the signs of our permutations respect composition, and that's something that we're going to need in our formulas.